Hello, this is Prof. Nays again. One of the review topics we're going to do in this little mini session is partial fractions, which you did in Calculus 2. So it's probably worth going over again because my guess is you have not seen it in a while. So we're going to do two types. Okay, so let's get started. Um, so very first, this is what partial fractions is about. Suppose you have, let's say, 1x minus 4x plus 7, and you want to write this out as a sum of two fractions. Now what this is like the reverse of the common denominator trick. Now the method I'm going to show you, uh, the astute observer will realize that I'm papering over two key details. First of all, how do I know it's just going to be A and not something else? I'm not going to explain that. And the second, when I go to actually solve this for A and B, I'm going to be into using up the number 4 and the number -7. And philosophically, there's a problem there. Practically, there really isn't. Now, the way you do that is you try to get a common denominator on this side. So it's ax plus 7 plus b x minus 4. So now we have a common denominator, and that must equal this. And here's what you can do. This has to be equal for all x. Now you might say, well, x equal 4 and x equal -7 isn't in the domain, but we're going to be engineers here and not worry about that. So let's just look at this thing here. And it does work when you do limits, but I don't want to get that involved. So first of all, to solve this has to be true for all x. Let's use x equal 4. I know that's illegal, but it's going to get us what we want. So if I put an x equal 4 here, this is a 0, and I get 1 is equal to a times 4 plus 7 is 11. So a is 1 over 11. That's nice. That was not very fussy. And 2, let's use x equal -7. So 1 is equal to b. You plug in -7 here, you get a 0 here. So 1 is equal to minus 11b, and b is equal to -1 over 11. So in fact, you have that 1 over x minus 4, x plus 7, is equal to 1 over 11, 1 over x minus 4, minus 1 over 11, 1 over x plus 7. Okay, now that was kind of an elementary one. Now let's use one that's a little bit more challenging. And let's say we had x over, let's say x squared plus 36. And let's say x minus 2. And we now want this to be a plus bx over x squared plus 36 plus c over x minus 2. Now you do need both of these because this is a quadratic and you cannot factor it. That's called being irreducible. This has to be a degree 1 polynomial. So what you do is you factor out as much as you can, and then what you have here is always going to be 1 degree less than this, provided this one can't be factored any further. And that's what we have right here. So these are equivalent to the prime factors. So if we clear the denominators like we did before, multiply this by x minus 2, and we multiply c by x squared plus 36. That's what we have. We want to somehow make these 0. So what I'm going to do, because we're going to use complex numbers in this course, I'm going to use complex numbers here. Now, for this one, I'm not. Let's use, this has to be true for all x. So let's use x equal 2 first. So plugging in x equals 2, we have 2 is equal to c, 2 squared plus 36. Or we see that c is equal to 2 over 4 plus 36, which is 2 over 40, which is 1 over 20. So we got our c there. That was easy. Now, to get the second one, let's go ahead and use complex numbers. So what will make this 0 right here? And I'm going to use x equal 6i. Then x squared is 36 times I squared, which is minus 36. So let's use x equals 6i. So if I do that, I get 6i is equal to a plus b times 6i times 6i minus 2. Now, it's a fact about complex numbers is that they are equal where the real parts are equal and the complex parts are equal. So the 6i is equal to, let's distribute this, a times 6i plus b times 6i times 6i minus 2a minus 2b times 6i, where 6i is equal to a times 6i minus 12b times I. So we got that one and that one. And then we have minus 2a. This is going to be minus 36b because I times I squared is negative 1. So now, hidden in this, I want to rewrite this. 6i is equal to a minus 2b times 6i. That's this part here. And then this part right here is going to be minus 2a plus 36b. Now we actually have two equations hidden here. These two must match. This is called the imaginary part. This is a 6i. That's a 6i. Therefore, this a minus 2b must equal 1. On the other hand, there's no real part here. This is a real part. So you also say that 2a plus 36b is 0 divided by 2. We get this right here. So now when we want to finish this up, let's use this part right here. 18b is equal to minus a, or b is equal to minus 1 over 18a. Now let's plug this in right here. A minus 2, well, b we said is minus 1 over 18. A is 1. So we have a plus 2 over 18 is 1 over 9. Or we get 10 over 9, a is 1, or a is 9 over 10. So we got that. So now our b is minus 118, 9 over 10, which is 9 divided by 18 is 2, so it's minus 1 over 20. So we have a value for A. We have a value for B. Our C we discovered was 1 over 20. So when we take this and plus it down here, remember C is 1 over 20. So this is equal to, we get our glorious answer here, 9/10 minus 1 over 20x over x squared plus 36. And then plus 1 over 20x minus 2. So that's our, now again, this is hardly a wonderful, good expression. What we actually do to make this look a little humane, more humane, is let's take out this 1 over 20. So then 9 over 10 is 18 over 20, so I get 18 minus x over x squared plus 36 plus 1 over x minus 2. And that looks a little bit nicer here. And that's how you do partial fractions. So thanks for watching.